When a Linux system says the disk is full, the natural reaction is to assume you simply ran out of storage space, delete a few files, and move on. That works sometimes, but the reason this topic matters is that disk full incidents often behave like puzzles, where the obvious explanation is not the real one. You might see a report that says only a small percentage of space is used, yet the system still refuses to write, or you might delete a large file and still see no improvement. You might also discover that normal services start failing in odd ways, not because they are broken, but because they cannot create temporary files, write logs, or update small state files. The first response goal is to avoid random deletion and instead figure out what kind of full you are dealing with. Once you learn the patterns, you can classify the situation quickly and choose a response that actually restores stability instead of just rearranging the mess. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A useful starting point is to understand that disk full behavior can come from at least 3 different constraints that feel similar at the surface. The most obvious constraint is capacity, where the file system has no free blocks left to store additional data. A second constraint is inode exhaustion, where the file system still has space but has run out of inodes, meaning it can no longer create new file entries even if the files would be tiny. A third constraint is runaway logging or runaway writes, where something is generating data faster than you expect, and the disk is filling as a symptom of a deeper operational problem. These 3 scenarios can look similar because the end-user symptom is often the same: failures to write, failures to start services, and error messages that mention lack of space. The difference is what you should do next. If you treat every case as simple capacity, you can waste time, delete the wrong things, or even remove evidence you need to fix the root cause. Capacity exhaustion is the scenario most people imagine, and it is still worth describing carefully because it has its own tricks. In capacity exhaustion, the file system simply has no place to put additional data, so any operation that needs to allocate new blocks fails. That includes more than saving a large file. It includes writing a small lock file, updating a database journal, or expanding a log by a single line. Beginners often focus only on the largest files, but a service can fail due to tiny writes that happen constantly, like updating status files, caching, or maintaining indexes. Another trap is that even when a file is deleted, the space might not become available if a process still has that file open, because the file system may keep the data until the last handle is released. This creates the confusing situation where you think you removed data, but the system still behaves full. The right mental model is that capacity is about allocation, and allocation depends on how the file system is currently holding on to space, not just what you can see in a directory listing. Inode exhaustion feels like a magic trick the first time you see it, because it breaks the usual assumption that deleting a few large files is the best fix. An inode is like a record that describes a file, storing metadata such as ownership, permissions, timestamps, and pointers to where the file's data blocks live. Many file systems allocate a fixed number of inodes when they are created, and while that number is usually large, it is still finite. If a system creates huge numbers of small files, it can consume inodes long before it consumes significant storage capacity. This is common in places where applications create per-request temporary files, where caches are implemented as many small objects, or where misbehaving processes generate endless tiny log fragments. The symptom is that you cannot create new files, even though free space appears available. Beginners sometimes suspect permissions or a broken disk because the behavior feels inconsistent, but the reality is that the file system is out of file entries, not out of blocks. Solving inode exhaustion requires you to reduce file count, not just file size. Runaway logging is another frequent cause of disk full incidents, and it has a distinctive operational smell once you learn to recognize it. Logging is supposed to be a helpful record of system behavior, but when something breaks, logging can explode because errors repeat rapidly and each repetition is recorded. A service stuck in a restart loop can log the same failure thousands of times, and a misconfigured debug setting can produce far more detail than intended. The tricky part is that logs are often written to locations that are essential for system stability, and when those locations fill, the system loses the ability to record what is happening right when you most need that evidence. Runaway logging can also masquerade as other problems because it may fill not only the primary log directory, but also temporary directories, queues, and caches that depend on writable storage. The right interpretation is that the disk full condition is the symptom, and the underlying cause is usually a repetitive failure that is generating data as a byproduct. If you only delete logs without addressing the repeating trigger, the disk will fill again quickly, and you will be right back where you started. One reason disk full situations feel so chaotic is that storage is tied to almost everything the system does, even tasks that seem unrelated to storing files. Many processes rely on temporary files for safe updates, on small state files to coordinate locks, and on caches to maintain performance. Even authentication and package management can fail when they cannot write small changes, and service managers can struggle to start or stop units because they cannot update runtime state. This is why a disk-full system often behaves like it is sick in multiple organs at once, with failures popping up everywhere. The first response triage mindset is to stop interpreting those failures as separate root causes and start treating them as downstream effects of a shared constraint. When you restore enough write capability, a surprising number of errors disappear on their own because they were simply consequences of being unable to create or update files. That can feel like magic, but it is really just the system regaining its normal ability to record state and progress. Your job is to identify which constraint is binding and restore headroom safely. A particularly confusing disk-full puzzle is when you delete a large file. The directory looks smaller, yet the file system still reports little or no free space. One conceptual reason this happens is that processes can keep a file open even after it is removed from the directory structure, which means the data is not fully released until the process closes it. Another reason is that some files are created in places you do not think to check, such as temporary locations or application-specific directories, and deleting something in one area may not touch the real consumer. A third reason is that certain file system features may reserve space for system safety. So a normal user might experience write failures earlier than the point where the disk is literally at absolute capacity. Beginners sometimes respond by deleting more and more data indiscriminately, which can remove useful diagnostics or even application data and still not solve the actual allocation problem. A better approach is to slow down and think about what is actively writing and what might be holding space invisibly. Disk-full triage is partly about storage and partly about process behavior, so you need both lenses. Another common puzzle is when the disk looks full, but the growth pattern does not make sense relative to normal activity. This is where baseline thinking becomes valuable, because most systems have recognizable storage rhythms. Logs usually grow at a steady pace, caches grow until they hit a limit, and databases grow in relation to workload. When a disk fills unexpectedly quickly, that usually indicates a change in behavior, not a gradual trend. The change might be a new service producing unexpected output, a configuration change increasing verbosity, a sudden loop generating files, or a backup job writing to the wrong location. A beginner misunderstanding is to treat the disk as the failing component, when in many cases the disk is simply doing exactly what it was asked to do, storing an abnormal volume of data. The operational skill is to look at what has changed in the system's behavior and match that change to the storage growth. When you connect growth to cause, you can fix the root problem and prevent a repeat incident. Inode exhaustion has its own set of confusing behaviors that are worth calling out, because it can cause errors that sound like capacity issues even when the disk has free blocks. When the file system cannot allocate a new inode, it cannot create a new file entry, which breaks many operations that do not feel like storage operations. Creating a temporary file, creating a new log file, or creating a new small cache object can all fail, and programs may report generic write errors that do not explicitly mention inodes. A subtle point is that inode exhaustion can be accelerated by patterns that create many short-lived files, because even if each file is tiny, the cumulative inode count can climb rapidly. Another subtle point is that deleting a few large files may not help at all if the large files are not the ones consuming the inode count. The effective fix is reducing the number of files, especially the explosion of tiny files that often happens in misbehaving caches or uncontrolled temporary directories. This is why the correct response depends on classification. Inode problems are about file count pressure, not size pressure. Runaway logs also have a special danger. If the system cannot write logs, it becomes harder to diagnose what is happening, and the next incident becomes more expensive. A disciplined environment treats log growth as a managed resource, with retention limits and rotation behaviors that prevent any single log from growing without bound. The key concept for a beginner is that logs are not meant to be infinite, and healthy systems prune or archive old logs to maintain space. When runaway logging happens, it often reveals that the safeguards were missing, misconfigured, or overwhelmed by an abnormal event. Another important concept is that runaway logs often point back to a real error that is repeating, such as authentication failures, a missing dependency, or a service that cannot connect to a required resource. The logs are telling you the truth, but they are telling it too loudly. A strong response restores disk headroom while also identifying the repeating root message that is driving the explosion, because fixing that message is how you stop the growth from immediately returning. It is also helpful to think about where disk-full problems tend to concentrate, because certain directories are designed to be write-heavy and therefore become failure hotspots. Temporary storage locations are frequently used by many applications for intermediate work, which means they can fill without any one owner noticing. Log storage locations are designed for continuous appending, which means they can grow steadily and then spike during failures. User home directories can fill through downloads, caches, and large artifacts that feel harmless individually but accumulate over time. Application data directories can fill through normal growth, but they can also fill through abnormal behavior such as repeated retries or unbounded queue files. The point is not to memorize a path list, but to develop a habit of thinking in categories. Where do transient files accumulate? Where do append-only files grow? And where do persistent data stores expand? When you reason in categories, you can spot the likely suspects faster, and you are less likely to delete the wrong data in a panic. Disk-full incidents reward calm classification more than aggressive cleanup. A mature approach to disk-full risk includes designing for headroom, because the system behaves better when it has breathing room. Headroom is the free space and free inode capacity you intentionally preserve so routine operations can continue even during bursts. Beginners often treat free space as wasted space, but in operations, free space is stability because it allows logs to record failures, allows services to restart, and allows the system to manage temporary work safely. The same idea applies to inode headroom, where you want enough free inodes so the system can create files during normal peaks without suddenly failing. Good monitoring and alerting tie directly into this, because you want to detect trends before they hit the cliff, and you want alerts that trigger while you still have options. When you wait until the system is already failing, recovery is harder and riskier because you might be forced into emergency deletions without enough time to evaluate impact. Headroom is what turns disk full from a crisis into a controlled maintenance activity. When you respond to a disk full incident, you also want to be careful about the difference between freeing space and fixing the cause of consumption. Freeing space is the immediate action that restores write capability and stabilizes the system, and it may involve removing unnecessary data or relocating large files, but that is not the end of the story. Fixing the cause means identifying why the disk filled, which might involve correcting a misconfiguration, adjusting retention behaviors, stopping a runaway loop, or addressing a failure that triggered excessive logging. Beginners sometimes stop after freeing space because everything looks normal again, but that often leads to repeat incidents because the underlying behavior is still present. The most reliable systems treat disk-full events as learning opportunities to improve guardrails, such as enforcing retention, ensuring caches have limits, and establishing clear ownership for storage growth. This connects directly to professional operations thinking. You do not only restore service, you also reduce recurrence. When you build that habit, your future self spends less time firefighting and more time improving reliability. To bring everything together, the disk-full puzzle is really about understanding what constraint has been exhausted and what behavior created that exhaustion. Capacity exhaustion means the file system has no free blocks, which breaks any operation that needs to allocate more space, even tiny operations that feel unrelated to storage. Inode exhaustion means the file system has run out of file entries, which prevents new files from being created even when block space still exists, and it often comes from an explosion of tiny files rather than from a few large ones. Runaway logs are a special case where repeated failures or excessive verbosity create rapid growth, turning disk space into a symptom of a deeper issue that must be addressed to prevent immediate recurrence. First response triage is the discipline of classifying which full you are seeing, stabilizing the system by restoring headroom safely, and then tracing the growth back to the generating behavior so you can fix it at the source. When you learn these patterns, disk full events stop feeling like random disasters and start feeling like solvable, evidence-driven problems, which is exactly the kind of reasoning Linux Plus expects you to build.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.